Yeah, we started with what is AI, what is ML and DL, the difference between them, what we can do with the AI, what we can do with the ML, what we can do with the DL, and how they differ. It is simply in machine learning, in traditional ML, we can handle only structured data sets. It is not possible to work with the unstructured data or semi-structured data like um, images, audio files or video files. This kind of data set we cannot work with. That is deep learning. In machine learning, what we do is we work with a structured data set like tables, that is columns and rows, where let me go back here, that Excel sheet. Yeah, where we have data which looks something like this from here to here. So here, if you want to draw any uh, insights or to predict something from the model, then we use machine learning. For example, for this particular use case, the data set that it shows is if this B is the column that shows the experience and C is the column which has the output variable salary. So this output variable also, it is depends upon the problem statement that we will have to decide which is the output variable, right? So here there are two possibilities. What is for that is one is the for a given experience, what would be the salary? That is what is the that can be the problem statement, or reverse order. For a given salary, what could be the experience a particular employee has? So both are possible. So depending upon the problem, the statement or the query that you are going to answer using your model, then depending upon that, you will have to decide the output variable. So here, if you see, this is the employee one with some rows, that is experience 1 year and salary is 30. And don't focus on this one, only till this point. B and C you can focus. And employee 2 with experience 3 and salary is 50. Employee 3 with experience 5 and salary is 70. So if this is the input data or the data set you have, then your uh, your aim here is to answer query like or predict for a given experience what would be the salary of the employee. This is the problem statement. Then obviously column C would be the output or the target variable that you will assume, or you will take it as the you will consider it as the output variable. That is what is the problem statement here. So we had discussed this, and then there are two main uh, problems that we solve in machine learning always. That is, one is regression and another one is classification. So what is the difference is, for example, here in place of this C column output variable, instead of this kind of numerical data, if there is something like, let us say, uh, uh, this employee belongs to band 1 and this employee belongs to band 2 and this belongs to band 1, something like this. So this is something like band 1, band 2, band 1 again, or band 3 may be there. So these bands are something kind of classes or categories that are present in the data. So for a given input data, it could be experience and salary, then the employee falls under band 1. For a given experience and salary, the second employee falls under band 2. So if this is what is your output, or if you have to categorize the input data points into one or more, one of the categories that are present here in this column, then this is classification problem. And the classic example for this classification problem is for if the given image is belongs to a dog or cat, cat dog classification problem. or you need to identify whether there is a signature, handwritten signature present in the input document or not. That is also classification problem. So you will see a lot of classification problems, both in numerical as well as other formats, unstructured formats as well. So classification is nothing but you need to classify or categorize the data into classes or the classifications depending upon the um, input rows, or for a given data point you need to identify to which class it belongs to. That is what is classification. Whereas in case of regression, we don't do that. We will predict one numerical value. We will predict one output target variable like this. For example, we have built a model, regression model, and for this one, the input is, let us say, experience is the input. It is giving us yeah, prediction. That prediction is salary, let us say. So what is salary? This is numerical value. So if you are predicting, or if your output variable is numerical value, then it is going to be a regression use case. That is why the name regression? It is because, let us say, you have some data points. You can draw the line like this. Let us say this is in what is the independent variable here? Experience, right? So this is the input. So we can take something like 1, 3, 5 on x-axis, and on y-axis it is first one is 30, 50, 70, and for 1 it is 30, so I'll take this point, and 3 it is 50, so I'll take this point. I'll take for 5 it is 70, so somewhere here. So what I can do is I can draw a line, so which is something like this. And for any given unknown input, which was not there in this training data, we call it as. So let us say in future you will have to answer what would be the salary for a experience of 15. Then you will draw a line which is something like this, and you will check where it is intersecting with the this line, right? So basically what you are doing here is you are extrapolating this line, and wherever it meets this point, that is what would be the corresponding salary prediction for this 15 years experience using this model that you had come up with. That is why the name regression, you are extrapolating it. That is fine. So this is classification and regression. So you will see, if just you need to check if the output variable or the prediction that you are going to make, whether it is numerical value or what it is, what you need to do. You need to classify. So majority, there are few other types of problem statements available, like clustering we do, and also segmentation. But all of them are under nuances of classification problem statements, I can say. That is one thing that you need to understand. So it's okay. So now this is the input data that you have, And this is the predict. How do we go about training? That is what we were discussing from last day, right? So if you see in the first, this is the input data set that you have, that is experience and salary. So you need to build a regression model here. You need to build a regression model here. So we will discuss generic steps that we follow to train a machine learning model. Any problem statement, it can be regression, it can be classification. We'll discuss generic steps that we follow. So first what we do is here, because this is a regression use case, we will say this was the input, this is the input data point, and corresponding output was somewhere here. So what I do is, this is the line, that equation that we need to, for this one, this is one, and let us say corresponding point, this is the one. I don't know value, just I am writing it here, somewhere here. So this is the value. What I can do, let me take this point and remove this, because we don't have the line yet. What we have is this data points only, and correspondingly this point, and then corresponding value is this point, data point. This is for this experience, this is the salary, so this is the coordinate point that I have come up with. So ultimately what we need to do now is, when I say we are building machine learning model, I need to come up with this line, which is at least uh, hugging the data points, hugging the data set closely as much as possible. So again, repeating, when we have this data points with us, when I say I am building machine learning model, I mean to say I need to come up with this line equation, y equal to mx plus c, and with values for m and c. I need to have, that is something like y equal to 20x plus 50, or 2x plus 7, something like this. I need to come up with. That is what we call it as model. What is a model? Model is something, for a given input, it has to predict the output. That is what is a model is, right? So here, if I give x, that is if I give experience in this use case, then it can predict the salary, y. So this is the model. This is the line equation that we need to come up with when I say we are building a machine learning model. So I hope model concept is clear to you. So again, if you have any questions, please feel free to ask, because I am not able to understand whether you are getting my points or not if you don't say anything. Till this point, is it clear? So this is the equation. When I say, when we are building machine learning model, this is the equation that we need to come up with. So next step is, how do we come up with this kind of equation? At least, and again, one more thing that you need to keep in mind is, we may not be able to get these kind of equations for each and every problem statement that we have in machine learning. It may not be possible. And particularly in deep learning, it is impossible to get this kind of equations. What we will get is maximum is the parameters, weights and bias of the model. So don't always think that we will need this kind of equation to when we say we are building a machine learning model. It is in machine learning, there are three, right? Machine learning, deep learning, and generative AI. Only in machine learning, you will be able to see at least some sort of equation that is coming up in when you build a model. But in deep learning and generative AI, it is impossible. So that is why they say machine learning is more interpretable, more explainable. When you see the equation, you will be able to explain why your model is predicting something like this. More interpretable, more explainable machine learning. But deep learning models are not interpretable, not explainable, because we don't have any such. There are frameworks that are extensively used to uh, bring up some sort of explainability or interpretability to your problem statement. But inherently, that is within the model, it is not possible to explain using any of the parameters or equations in deep learning. Uh, it's that we will see later, but yeah, this is the equation that you need to come up with here now. So how would we get this equation is the question now. So first, what we do is even if you think of it, like how would you come up with this? Is you will initialize random values for m and c, random values for m and c. That is initialize weights or parameters. M and c are the parameters of the model here. And then, so let us say you had something like 0.1 and 0.5. These are the values that you had initialized for m and c. Then what would be the y value? So y equal to, it is 0.1 into x plus 0.5. This is the y, right? So now if you substitute values for x, let us go back here a little bit. This is not visible now. 0.1 and 0.5, right? So let's do this. X calculator. This is better. Yeah, y equal to 0.1 into x plus 0.5. This is the output because you had instantiated or initialized parameters m and c as 0.1 and 0.5. So what is the data set that we had? It is for a given experience 3, experience 3, and what would be the salary? This is what is the data set, right? So 3 and 20. Let me create one more data set here. This is the data set we had. This is salary. So if you substitute these values here, y equal to, or I can say, what would our model predicts? If we substitute 3 here, 0.1 into 3, 0.3 plus 0.5, it is 0.8 is what we are getting. And if you substitute 5, 0.5 plus 0.5, it is 1. If you substitute 7, 0.7 plus 0.5, so it is 1.2 is what you will get. This is what is our model. This model is predicting if you substitute values. So there is a huge difference between our prediction and what is the actual value. This is the prediction and this is the actual value, correct value or the ground truth value. So what we do is we calculate the total error. I am writing it as T, and then we'll try to adjust it. For that, what we need to do, first thing is I need to calculate error. And what is the error? It is error is equal to, how do we calculate error? Y actual minus Y pred. I am writing it as here. And this Y represents Y actual, this one. And this is Y pred. So 20 minus 0.8, that is 18.2, right? Or 19.2, sorry. And 50 minus 1, it is 49. And 80 minus 1.2, it is 78.2. So this total we will calculate here. Total error is equal to what it is. And then once we have this, what we do? Next step is adjust these weights. Adjust these weights. What is happening here? There is a huge difference. So we need to increase this parameter. So we will increase these parameters by, let us say, we had decided that we will increase this parameter and this parameter by 0.5. So then again, we'll come up with new model now because models have parameters have changed. So that is delta, or we call it as learning rate basically, that is 0.5. I'll discuss about this parameter later, but you, as of now, you can imagine that the delta, or how much value we want to increase this by, this one 0.5. So 0.6 would be the final value of M. If I increase 0.1 by 0.5, then 0.6 plus it is going to be 1. Still, it will be really less. So anyway, you can imagine, like salary is 20 into 0.6, it is going to be 1.2, and this is going to be 2.2. That's all. So we need to increase it by, let us say, 5 rather than 0.5. Let us make it as 5. So this comes out to be 5 plus 0.1, it is 5.1. Let me write that here, 5.1, or else let us make it as 5 only as of now, so that it will be easy to calculate. This is 5.5. This is okay because we will just add it. So what would be the new prediction that we will get? Let me write that data set one more time. Those 3 points, 3, 5, 7, and then 20, 50, 80. 20, 50, 80, right? So now what, this is the Y value, actual value. And what would be the prediction? What would be the prediction? So X is 3, 5 into 3, 15. 15 plus 5.5, it is 20.5. And then 5 into 5, 25. 25 plus 5.5, 30.5. And 7 into 5, 35. 35 plus 5, 40.5. So you can see total error might have come down a bit. This error, if you write here, error is equal to Y minus Y pred, and that is given by 20 minus 20.5, 0.5 minus 0.5, 50 minus 30.5, it is 19.5, and 80 minus 40.5, it is 39.5. So total error might come down compared to earlier. But the thing here is, how did I come up with this value? Or else, how do we iterate it over? Like how long you will iterate? For that, how long you will iterate question is simple. How long you will iterate? Till you reach some minimum error value, total error value. What you will observe is you will keep on changing the values for coefficients or the parameters and then observe the total loss or the error, whether it is coming down or there is no change or increasing. In these two scenarios where the total error or the loss function we call it as is not coming down or keep increasing, then we will stop it. We'll stop changing those values because we are not making any progress. Model is not able to learn, we say. This is what happens. But if you have to do this programmatically, what would be the steps that you follow? But that is why if you see what we have done, we had initialized the weights and then we got the predictions. We substituted those values, input data points in the model equation and then got the prediction and then calculated the error. Here again, one more thing, I think I discussed in the last session also, how we are calculating this total error. We are calculating for the complete data set that we have. That is complete data set, whatever we had. Let us say if we have 100 data points here, we calculate total error for 100 data points. Then this is called batch gradient or vanilla gradient, batch gradient. And what we do is, for example, if you have another scenario is, you had 100 data points, but you divided it into 20 by 15, 5 batches of 20. Then that is called mini batch. You are not considering complete data set as single batch. That is why it is mini batch gradient descent. And you consider to, again repeating why I am saying this is people get confused here. You are calculating total error for complete data set and then adjusting the weights. Then that is batch gradient. You are calculating error for a mini batch, total error for mini batch, and then adjusting the weights. Then it is mini batch. You are calculating error. You cannot say total because here in this case, single data point we take. You are calculating error for that single data point and then adjusting the error. Then that is stochastic gradient descent, SGD. Why this gradient descent is coming? It is, we'll discuss that. Is this clear till this point? We initialize the weights. We initialize the weights and then calculate what it is giving, that is prediction, by substituting the values, those parameters, that initialized parameters in the line equation and get the prediction and then calculate the error. How we are calculating? These three methods that you can follow. You can calculate the error for complete data set and then adjust the weights, or else you can split the input data into some small batches and then calculate total error for that and then adjust the weights, or you can calculate error for single data point and then adjust the weights. It is up to you. Ultimately, your goal should be to minimize that error. That's all. I think here we have this plain, or you can say batch SGD and batch gradient descent. Sorry, not SGD. Gradient descent. Mini batch gradient descent it is. Any question to this point? Now comes the main part actually. What is gradient descent? How do we adjust the parameters? So as I mentioned, if we use this earlier also, like we have discussed, here instead of these values, let us say you had predicted there is one situation, just to explain you why we need a different loss functions. Let us say this is the y value that we had, and those values are 1, 2, 3. And our model is predicting y pred as 1.5, and this is 1. Our model is predicting it as, and this as 3.5. So if you calculate the error here for this particular scenario, error is what? Y minus y pred, right? Y pred. 1 minus 1.5, 0.5, minus 0.5. And 2 minus 1, this is 1. And 3 minus 3.5 minus 0.5. So if you calculate the total error, that comes out to be 0, right? 1 minus 0.5 minus 0.5. So total error is 0. But is it correct? Like, we are not predicting exactly. The model is not perfect, but still we are getting total error as 0. So for this, to avoid this kind of scenarios, we don't use the error as y minus y pred. That is one thing. And one more is, if in machine learning or deep learning, basically in this AI domain, this is something called as loss function or error function. uh, and this error function should be differentiable at it should be a differentiable function. This function, if you see, it is not differentiable at one of the point where it may look something like this. Why I am saying it looks something like this is, if you want, you can substitute it. Y equal to, sorry, YP, basically, prediction, right? YP is equal to MX plus C, right? That is what is the model is. YP is equal to MX plus C. And this M value, maybe for this particular calculation, it can be any some specific value like 0.1 uh, into X is constant. X is constant here. That is what is you need to take care. X is the input value, right? So this is constant, but M and C are the variables here. So just for the sake of simplicity, let us assume that your model is passing through origin. In that case, you will not have this constant term, only y equal to mx. So it may be something like this, right? So it is passing through the origin. Then you can interchange, like this is the x is the constant here, m is the variable, right? So if you see, if you take this point, if you substitute this value here, y minus mx is the value that you will get. And if you try to draw, what is the dependent variable here? This is error, right? Y equal to mx, y minus mx. And y, if you see, this y is what? Actual y value, actual prediction, this one. That is also constant. It is not changing. It is always fixed. This y value, output variable. So this is fixed. So this is fixed. This value is fixed. And this x value is also fixed. This x initially like 1, 2, 3 or whatever inputs that are there. This is also fixed. Only variable is m here. So the output or the model may be something like this, or it can be something like this, or it can be something like this also. with the different slopes, basically, I am saying. So what is so if you draw a line which is which looks something like this, let us try this out. Error function, what would it comes out to be? 2 minus uh, maybe zero point 0.1 x is not taking or what? Multiplication, and yeah, it might look something like this. So this is fine. We don't have any issue with it. Main issue is with this one only, where we will get total error as 0. Where is this escalator? Yeah. For this particular scenario, the line equation is here. You can see this line equation. So this is not an issue for us. But where the scenarios when you don't have this value, the C value as 0, then it will be something like this. That I need to, what we can do is to show that in Desmos. As of now, I am writing this. This is the Y value I have assumed, and this is the M value, sorry, X value, and this is the slope value. Slope is not constant here. So if we add another variable, it is not possible to draw here in Desmos. So it is fine. So to avoid that, what people have done is people have come up with this equation. Just square it before you calculate it. So if you square it, this comes out to be this and 1 square and 0.5 square. Now if you calculate the error, 0.5 into 0.5, it is 0.25. Minus into minus plus. So 0.25 plus 1 plus 0.25. So it is 1.5. The error is 1.5. So sum of squared errors we call it as. So this is the error, and the squared error is this one. We are squaring it and identifying or calculating the sum. That is, rather than total error, it is better to call it a SST, I think. Sum of squared errors. SSE. So this we will use, and the curve or loss function, we call it as, sorry, it may look parabolic, which is smooth. It is differentiable at each and every point. And if you substitute those values here in this equation, let me derive that one as well. That SSE, sum of squared errors, SSE, is loss function, we call it as cost function, loss function, everything is same. So here y is fixed anyway. This is fixed. And y pred, what is y pred? That is m x plus c whole squared. That is equal to y minus m into s minus c whole squared. That is equal to, here you need to always observe what is fixed and what is variable or what is changing here. Y is fixed because this is the ground truth, and the slope, the slope value, it is variable. For that I am writing v. And x value, this is also fixed. It is coming from the input data set. So this is fixed. And c value, this can change. C is nothing but the intercept actually. So the line can be like this or something like this or something like this. So for each and every line that I drew just now, it has different intercepts. So this is variable. C is variable. So if you draw, uh, if you interpret this, or if you draw it on the coordinate geometry, a coordinate plane, how does it look like? Is here there are three variables basically. That is, one is SSC, that is dependent on this X and C, sorry, this M and C. So I may not be able to show it in the test note. So what I do is usually, let us make this as 0, this C as 0, then just to represent it on two dimension coordinate plane, mx, y minus mx whole square. Then you can see it here. Let me remove few of it. I think we don't need this. This one also. So it is just y minus mx whole square. So it is same. Here y is constant. So in place of constant, I am writing 2. And slope is not constant. And x is the constant. So that constant x, I am writing it as 0.1. And in place of m, I am writing x. And all of it has to be squared. This is not squaring, it is power. Yes. So the last function, it might look something like this. It is a parabola, which is passing through the origin. So this we call it as last function. And here you can see for a given value of m, for a given value of m, let me write this here so that it is explicitly mentioned. Here, this axis, this y-axis, it is representing sum of squared errors. Why? Because here on the left hand side, it is SSE. And on the x-axis, what we have is, what we have? This y is fixed. That is, I had fixed it to 2. And the x value is fixed. And m is the variable here. The slope is the variable. So this axis, it is representing slope of the line equation that we are going to come up with. So if I draw that here, both of them. So what is happening here is, this is the x value that we had, some values, and this value, and corresponding y values were something like this is one data point, and corresponding to this is another data point, and corresponding to this is another data point that I had somewhere here. Okay. These are the 3 data points, let us say I had as input. Now, what I am doing here is, initially I had come up with a line equation or model which looks something like this. there sum of squared errors may be high. In the next iteration, I will adjust my line equation something like this. For this, SSE 2, let us say, sum of squared errors for this line and a sum of squared errors for this line. E will be SSE 1. And I come up with another line equation in the third iteration, which looks something like this. That is SSE 3. So here, SSE 3 will be less than 1, right? Because SSE 3 is almost hugging each and every data point in the input. So because here the slope of this one, M1, and the slope of second line, this is M2, and slope of this line, that is M3. This is steeper. This is more horizontal, right? So M1 is less than M2 is less than M3, right? So as the slope increases, sum of squared errors is reducing for this use case, what I have shown here. But here it is obviously it is reverse because this is not the exact data that I had taken here, right? So what I want to highlight here, why I am showing all of this is this equation that you see here. Let me move it little bit here. Yeah. Yeah. The parabolic curve that you see on the right hand side and the regression equation that this model basically you see on the left hand side, both of them are how they are related. That is what I want to highlight. That is why I'm showing it here. Here, very, very important thing that you need to notice is on y-axis we have sum of squared errors. On the x-axis you have this m value, and this we call it as loss function, this curve. So for a given m value, that is this line is fixed, then there is some m value to it. That is something like this. So what would be the error? How do you calculate? By substituting it here, right? So you will get it from this this loss function graph also. So if you are right now at this particular line, but you want to move towards this line in the next iteration when you are training, during the train, how would you move? That is what is all about gradient descent. Gradient descent tells us how in which direction you will have to move, that is in this direction or in this direction, to reach the this data set as much close as possible. Or in this graph, if you see in the loss function graph, to reach this global minimum, to reach the global minimum, how do you have to move? Like in which direction you will have to move to reach this point? That is what is gradient descent talks about. So I will spend some more time on gradient descent because that is the very, very basic building block of any machine learning algorithm. So there are many variations to it and very important. Any questions? Are first thing that I want to check is, let me check how many of you are there. Yeah, advice. Yeah, you are able to understand or not. That is what I want to check first. You are able to understand Are you are facing any issues at any point? If you don't speak up, like I assume I am teaching very well and I go with my own flow, it will be difficult for you only, ultimately, as the topics get complex. Okay, then I don't have any issues. Um, we'll drop off. Wait, wait. Thank you.